When we look back at the high-redshift universe, specifically past a redshift of 3, the prevailing astrophysical models predict chaos. We expect to see dynamically hot proto-galaxies dominated by violent collisions and clumpy gas. In these early systems, the kinetic energy is simply too high. This intense velocity dispersion actively prevents the gas from cooling and settling into the flat, organized disks we see in modern galaxies. Because those cold disks cannot form, the stable density waves required to create spiral arms shouldn't exist yet. The baseline assumption has been that spiral galaxies are entirely missing from this early epoch of the universe. That baseline is now being tested. Using data from the JWST Uncover and Megascience surveys, astronomers have isolated a single target that defies these models. They named it Alaknanda. Alaknanda is massive. It measures roughly 10 kiloparsecs across, and it sits at a photometric redshift of 4.05. Finding a 10 kiloparsec, highly ordered spiral structure merely 1.5 billion years after the Big Bang directly contradicts the expected timeline of galactic evolution. For decades, instruments like the Hubble Space Telescope faced a hard physical limit. Cosmological redshift stretches the optical light of distant galaxies deep into the infrared spectrum. Because of this extreme dimming and shifting, previous deep field surveys simply lacked the wavelength coverage required to resolve mature structural details at redshifts greater than 3. The James Webb Space Telescope bypasses this limitation. Its near-infrared medium band filters provide the precise resolution needed to peer into this epoch and capture the optical rest frame of these early targets. But seeing a faint spiral shape in an infrared image is not enough to rewrite our models. A smudge on a detector could easily be an observational artifact or a chance optical alignment of unrelated background objects. To definitively classify Alaknanda as a true grand design spiral, astronomers have to systematically deconstruct the raw light data. We have to mathematically strip away its ambient light, prove the underlying symmetry of its arms, and date its stellar population. The first step in this reduction uses parametric modeling, specifically an algorithmic tool called GALFIT, to isolate the underlying architecture of the galaxy. The algorithm begins by calculating the light of the bright central core, fitting it to a mathematical curve known as a Cirsic profile. Next, it measures the vast, diffused light spreading outward from that center, capturing this as a radially decaying exponential disk profile. In raw observation data, the central bulge and wide disk are so bright they drown out the fainter structural details. So the algorithm mathematically subtracts those modeled light profiles from the raw image, leaving behind only the residual light. What remains in that residual data are 2 distinct symmetric spiral arms spanning the width of the galaxy. Exposing these underlying density waves proves we are not looking at a chaotic clump of early gas. We are looking at a mature, rotationally supported system dominated by a 2 kiloparsec exponential disk. At extreme redshifts, parametric modeling alone can be fragile. To verify the disk's symmetry, astronomers apply a secondary statistical approach known as non-parametric morphology. This method ignores our visual assumptions about shape. Instead, it categorizes galaxies purely by how their light is statistically distributed across the image pixels. This chart shows the Gini M20 diagnostic plot, separating messy mergers from smooth disks by tracking light distribution. If we plot Alaknanda's exact coordinate, represented by the black star, it falls cleanly within the boundary defining stable disks. This is a plot showing the asymmetry versus concentration array, a second diagnostic test used to measure how symmetrically the light is weighted. Here again, Alaknanda plots tightly into the stable disk parameters, resting firmly below the threshold line that indicates a lopsided merger. Both independent statistical tests agree. The galaxy's light distribution is shallow and highly symmetric, statistically eliminating the possibility that this is a chaotic early universe merger. Even with its structure confirmed, determining the precise distance and age of Alaknanda presents a challenge when we lack a traditional optical spectrum to read. This chart shows spectral energy distribution modeling, fitting simulated spectra against light captured by JWST's filters, represented by the purple line. The tight grouping of these filters rigidly constrains the Lyman and Balmer breaks along the left side of the axis. As we move across the data, clear anomalies emerge in the F250M and F335M filters, where the observed flux significantly exceeds the baseline model. These specific flux spikes correspond to ionized oxygen and hydrogen alpha emission lines. Their exact positioning provides independent physical confirmation of a redshift of exactly 4.05. Isolating these specific emission lines reveals regions of active star formation, mapping directly onto the spiral arms in a highly organized beads-on-a-string pattern. The SED model solidifies the entire case. We now have a verified distance, a verified symmetric structure, and physical proof of actively star-forming arms. With the distance locked, the SED modeling yields Alaknanda's physical properties. It holds a massive stellar population paired with a high star formation rate of roughly 63 solar masses per year. But the critical output of the model is its timeline. The galaxy has a mass-weighted age of just 199 million years. Mapping this onto the cosmological timeline demonstrates that 50% of the stars in this massive system formed entirely after redshift 4.6. This discovery creates an extreme temporal constraint. Assembling 10 billion solar masses into a perfectly ordered, rotating structure required less than a few hundred million years. This timescale bypasses the prolonged clumpy settling phase theorized by previous models, proving that rapid disk assembly is physically possible in the early universe. A galaxy generally gains this kind of mass through one of two mechanisms: violent major mergers or smooth continuous accretion. Major mergers randomize star orbits, destroying delicate disks and leaving behind large spherical bulges. By contrast, steady streams of cold gas allow a rapidly spinning, perfectly flat central disk to form cleanly. Alaknanda possesses an incredibly low bulge-to-total luminosity ratio of roughly 0.14, practically eliminating the possibility of a recent major merger. This strongly points to rapid, smooth gas accretion, or perhaps a minor tidal interaction with a nearby satellite galaxy, as the main driver of its mass and its grand design arms. The remaining data needed to confirm this involves securing kinematic measurements via ALMA or NIRSPEC to physically track the rotational velocity of the gas. Alaknanda provides a concrete anchor for our understanding of cosmic structure. It confirms that the physical mechanisms driving galactic organization were operating with startling efficiency just 1.5 billion years after the Big Bang.